It's my pleasure to give this presentation. It's an investigation into corrosion-induced bond degradation with concrete and steel rebar with acoustic emission and 3D laser scan technique. So I'm now in School of Civil Engineering at Dalian University of Technology. So this is an outline of today's presentation. I will start with a background and introduction, then move on to the second part, experimental details, and followed by results and discussing, finally, conclusions. So for some civil infrastructure in marine environment, such as overseas bridges, island airports, and sea tunnel, ports and harbors, as well as those subject to the use of the icing salts in winter times. So the chloride-induced reinforcement steel corrosion is one of the primary causes for premature deterioration of concrete structures. So this slide, this slide just shows some corrosion happening in some typical structural elements. So we can see here is a bridge pier in the ocean water. There's some corrosion on the surface, and this is a bridge girder. And so we can see the spalling and the delamination of a concrete cover. And also this is for some concrete deck. And even for some steel structures with some painting, so the paint would degrade over time and so far off, so some exposed steel also corrode. So the last two pictures show the press stress tenders, the steel wires inside the tenders also corroded in the presence of water moisture, and we can see here. So it's protected by some grout, but also we can see some corroded steel wire. So corrosion, this slide just compares the corrosion cost between the USA and China. So the left pie chart shows the total corrosion cost in 2002 in the USA. It's around $276 billion. But this is almost 20 years ago. So this data is released by NIST International. A recent date is released in 2013. Its annual corrosion cost for highway bridges is around $13.6 billion. So in China, so this is a corrosion cost in China in 2014. It's around $194 billion. And for the highway bridges, roads, ports, and harbors, it's around $89.7 billion in 2014. So we can see corrosion is a big economic burden. It's almost around 3% of the GDP. And also corrosion is a safety issue. So on August 14, 2018, there's a marine bridge collapse in Italy, killed 43 people. And the corrosion of the steel strength is considered to be one of the possible reasons for this bridge collapse. And 68% of the strength in the primary group and 85% of those further out showed a cross-section reduction between 50% and 100%. So another event is apartment building collapse in Miami on June 21st, 2021. So we can see here this building collapse killed 98 people. And investigation by NIST expert also shows extensive corrosion found as one column metal is a foundation. So how does corrosion affect reinforced concrete structure performance? And we know that the volume of the corrosion products is usually 2 to 6 times greater than steel it consumed. So this expansive volume will generate some tensile stress in the concrete cover. As the tensile stress reaches the tensile strength, so concrete cracks. And second, the corrosion reduces the cross-section area of steel rebar, right? Also the mechanic degrades over time. Third, the corrosion damage the interface between the concrete and steel rebar. So this is today's topic. It focuses on the bond degradation. Actually, over the past years, many research have studied the bond degradation between the concrete and steel, but most of them pay little attention to the debonding process and the bond slip characteristics during the pro-out test. The second is the average corroding mass loss was used as the only index to quantify the corroding levels. But we know that for chloride-induced corrosion is typically localized corrosion, so this is not accurate. So last is bond strength is calculated based on the original steel bar surface instead of the recorded surface. That's because some accurate measurement techniques is not available. So in recent years, acoustic emission techniques have been widely used for structural health monitoring, especially to capture the signals during the structure like a damage process. And also with the advent of 3D laser scan, some accurate measurement is possible. So the purpose is, of this study is to investigate the effect corrosion on the bond degradation between concrete and steel bar. So with acoustic emission and 3D laser technique. So this is second part, experimental details. So in the laboratory, we fabricate the total of 18 specimens, including 3 reference specimens and 15 corroded specimens. So this just shows the dimension of these concrete specimens. And there's a concrete blocks, and there's a steel bar embedded inside the concrete. And also there are 2 epoxy-coated rebars were used as stirrups. And the concrete core thickness is around 41.3 millimeter. And to prevent the arcing effects and also the end restraint during the pro-out test, we also use 2 PVC pipes at this to end. So this just shows the plywood mold before pouring concrete. And the concrete we used as a water similar ratio 0.45, and the compressive strength is 32.4 megapascal. So after curing for 28 days, accelerated current tests were carried out. So the steel rebar were connected with a positive end of external power supply, while the other end was connected with a graphite rod, which inserted in a rebar side. To establish a corrosive environment, we spray 3.5 salt water periodically to keep the river side moist. And we can see here to monitor the electrical current flowing in this circuit, we use a data log system to record the electrical current. And so we can calculate the mass loss by using this equation. This actually is a Faraday's law. So the target corroding level in this study ranged from 0% to 35% mass loss. So this shows the pro-out test setup. Material test machine was used to carry out this test. The apply force is going down, and also we can see here this is a reaction beam, and also the rubber layer is placed between the concrete specimen and the ball bearing to prevent some stress concentration due to the uneven surface of this concrete specimen. And two DCVTs were instrumented to monitor the top slip and also the movement of the concrete specimen during the pro-out test. And also strain part were used to measure elongation, and the strain gauge to measure stress levels of the steel bar. And so this picture shows a test set up, and also 3 acoustic emission sensors were placed at the back surface and the 2 side surface to record the signal released during the pro-out test, especially the concrete cracking and the concrete steel friction. So next part is results and discussion. So as mentioned earlier, the corrosion will cause concrete core cracking. So for the specimens we investigated in this study, there are 4 types of crack patterns observed. There's one crack goes through the concrete cover, and 2 cracks penetrate through the two-sided surface, and also 2 cracks, one go through the concrete cover, and the other go through the side surface, and also 3 cracks. So this is a crack pattern. And also during the pro-art test, we record the surface conditions of these specimens. So this just shows the uncorroded concrete specimens. And this is pro-out force and slip curves, and at different load levels. And this picture shows, we can see here for uncorroded specimens, as loads reached 9.8 kilonewton, there's a crack initiates. And this crack propagates afterwards with an increase of slip. For corroded specimens, before the pro-art test, there's already a crack on the surface. We can see here, this is corrosion-induced crack. And this crack also propagates and increase with an increase of this the slip. And also, during the pro-art test, there's another crack initiated due to the loading. So this just shows we also measured the crack width after the pro-art test for the corrosion-induced crack. So this is a comparison of the crack width before the pro-art test and after pro-art test. So we can see here, before the test, the crack width increase with an increase of the mass loss of steel rebar. And after pro-art test, actually here, this is a width we measure it, and the width decrease exponentially with mass loss. And also this is just show the difference between the crack width before test and after test. We can see here it decreased non-linearly with an increase of the mass loss of steel rebar. And after pro-art test, we took out the steel rebar and we clean with a sandblaster, and we scan the surface with a 3D laser scan. So this just shows some scanned surface for uncorroded steel bar and the 3 corroded steel rebar. You can see here, obvious some corrosion paint on the surface of steel rebar, right? With an increase on mass loss, this corrosion peak becomes large, big. And we use some software to cut the scanned surface so we can get the radial cross-sectional area for this corroded steel rebar. So this in this study, we use 2 corrosion index to quantify the mass loss of a steel bar. One is eta 1, is the average corrosion loss. So this index is widely used by other researchers to quantify the mass loss. So for this one, we calculate the radial cross-sectional area loss, and we get the average area loss, and we substitute into this equation, you can get the average corrosion loss. And also the second is we call it a rebar corrosion loss, right? Because we know that for a bond between the steel and the concrete, the mechanical interlocking due to the steel rib is very important. So now we want to see how this rib loss affects the bond degradation. And so this is shows the calculation of this rib corrosion loss. This is A0 is a rib cross-section area before corrosion. So this is a shaded area for this one. And also after corrosion, we calculate the residual cross-sectional area for these ribs. So we substitute into this equation, we get a rib corrosion loss. So this table summarizes all the 15 corroded specimens, this information including the eta 1, eta 2, and also the crack informations. And we can see here, this one, this is eta 1 is area loss, and this is rib area loss. So we can see here, the rib area loss is almost greater than the average area loss, right? For example, if the average cross-sectional loss is 35%, the rib area loss reached almost 94%. So we also divide all these 15 specimens into 3 groups based on this mass loss, number of cracks, as well as crack width. It's a slightly damaged specimen, moderate damaged, and severely damaged specimens. So this is also some data we measured during the pro-out test. So this is the rubber deformation. There's a rubber layer, right, between the specimen and the reaction beam. So it's recorded by the DCVT2, and also this shows the load and the rebar strain curves during the pro-out test. It's linearly because the steel rebar is in elastic stage during the whole pro-out test. And so this is a load and a slip curves. And for this one, we use two slips. One is a top slip, which is recorded by DCVT1, directly the top of the top end of steel rebar. And second is a bottom end. So we calculated by using this equation. So this slide just shows the load slip curves for uncorroded specimens and 15 corroded specimens. We can see here. So this two is for the top slip. This is bottom slip. So we can see here for uncorroded specimens, there are three obvious stages observed during for the load slip curve. There's stage 1 and stage 2 and stage 3. And similarly for this one, there are also 3 stages. However, for severe corroded specimens, there are only 2 stages, stage 1 and stage 3. So, and we calculate the bond strength. Actually, it's a maximum bond stress by using this equation. So this just shows the relationship between the bond strength and the eta 1, eta 2, and the correct width. So this eta 1 is the area loss of the steel rebar. We can see here, the maximum bond stress decrease exponentially with an increase in eta 1, and it decreases linearly with an increase of eta 2. And for the correct width, and the maximum bond stress also decreases linearly, with an increase of the surface correct width. And okay, and this is acoustic emission signals during the pro-out test. And also we transfer this time domain signal into frequency domain, and we divided this signal into 3 stages, right? 3 stages corresponding to, okay, these 3 stages, 1, 2, and 3. So this shows a frequency plot for these different specimens. And there are 2 types of signals were acquired during the pro-out test. It's a high frequency range is due to the concrete cracking, because when we pro out the steel rebar, right, and there's some cracks because the ribs, right, ribs push against the concrete and cause some micro cracks. So this is concrete cracking. So the frequency is very higher. It's around 35 to 41 kilohertz. And also in the descending portion, the stage 3 is a low frequency range. It's due to the steel concrete friction. It's around 3 to 15 kilohertz. Okay, so this is a steel concrete interface morphology after the pro-out test for uncorroded specimens and slightly, moderately, and severely corroded specimens. We can see here for this one, for uncorroded specimens, there's some crushed concrete left on the steel ribs. And for this slightly corroded specimens, only a small portion of the ribs corroded and left on the concrete surface. For this one, I think the mass loss is greater than 20%. We can see the entire ribs corroded off and left on the concrete surface, and the steel rebar is almost smooth, right? Smooth. So, and we propose, actually we modified there's a model for the bond slip, and we modified this model from the literature, and we introduced the factors, reduction factors, and also alpha beta. So this model actually is corresponding to the 3 stages for the bond and slip curves: stage 1, stage 2, and stage 3. So this is the physical meaning of these parameters. So I will not talk a lot of details about this one. So we can see here. So this is the fitting results. So this contains the blue line is a fitting result with this modified model, and this is the measured result. We can see here the fitting result agree very well with test results for these 4 specimens. And after fitting, we can get some parameters. We extracted some parameters, and so this just shows the reduction factor, the relationship between the reduction factor and the corroding area loss eta 1 and eta 2. So we can see here, this reduction factor decrease exponentially with an increase of eta 1, and it decrease linearly with an increase of eta 2. So this eta 2 is a rib area loss. And also we recommended some values for the alpha and beta. These values for uncorroded specimens, and for the corroded specimens with mass loss less than 5%, and also for corroded specimens with mass loss greater than 5%. So these are some recommended values for this model, modified bond slip model. So this is actually the result in discussing. So finally, conclusions. There are 2 types of acoustic emission signals acquired during post-apparatus test: concrete cracking and steel concrete interface friction. And the bond strength decreased exponentially with an increase of the average area loss and the crack width. And it decreased linearly with an increase of rib area loss. And also finally, an empirical bond slip model is proposed to fit the bond slip curves. And the reduction factor exponentially decrease with eta 1 and linearly decrease with area loss of steel ribs. So actually, this study has been published in this Journal of Infrastructure Preservation and Resilience, and the open access, so you can download free from this website. And actually, this journal is the founding editor is Professor Xianming Xu on, I think it's March 2020. So this journal is the scope of the journal includes some planning, design, construction, inspection, monitoring, evaluation, retrofitting, and the reinforcing of infrastructure system, including roads, bridges, tunnels, building, airport. So you are very welcome to submit the paper to this journal. Thank you for your attention. I think that's all. Any questions?
Thank you, Dr. Tang. It's a great presentation. Does anybody have any questions for Dr. Tang? Just feel free to type in the chat box or directly ask here. Oh, by the way, Dr. Tang, would you please leave your contact information, like your email address?
Okay, sure. Hold on. Let me, okay.
Oh, we got a question from Yang Shenzhou. He asked, he said, "Thank you for your wonderful presentation, Professor Tang. Could you tell me about the role of the strain gauge on the loading side of your loading device?" Oh, the strain gauge. Actually, during a product test, we attached the 2 strain gauges on the steel rebar, and so I think the strain gauge is used to calculate the bottom slip. Let's go back to here. As I mentioned, right, we recorded the top slip and also we recorded the bottom slip. Actually, the bottom slip is the steel rebar, the deformation.
And so this is bottom slip is we use this equation. This is string part to measure the elongation, total deformation during a product test, and minus the elastic deformation of steel rebar. So this is strain gauge, and minus the deformation of the rubber layer, so we can get the bottom slip. Actually, I think the rule of this strain gauge is to calculate the bottom slip. We want to see the difference between the relative moments here and here. So that's why we use a strain gauge. Thank you. Any other questions?
I think Professor Tang has already left his email address in the chat box. Please feel free to shoot him an email if you have any further questions. And I will wait for another minute before moving on to our third speaker. Okay, so let's move on to our third speaker.